Transfer your funds into my account.
All right, here we go. So we're talking about, in this chapter, we're talking about matter. With matter, with this chapter, there's a lot more conceptual stuff and a little bit less math. Okay, and going forward now, when you do a lab or a test or something like that for significant figures and units, I look at the page and go, okay, there's 10 spots here where you would have sig figs and units. So 0 to 2, if you miss 2 of them, I'm not going to count any points off. If you miss 3 to 5, I'm going to count 2 points off. Okay, 6 to 10, I'm counting 2 points off. Oh, something like that. So there'll be a range. Okay, so I'll give you a couple freebies along the way, and then it's kind of a range, as opposed to the whole thing being about sig figs and units, because we've tested on that. We're moving on. Okay, now it becomes, can you apply those to these other situations? And I'm going to be testing those other situations and kind of looking and giving a nod to sig figs and units a little bit, but it's not going to be as intense as it was related to those. Okay, so we ease up a little bit, but we don't lose them. They're not gone. Okay, questions on that? The hardest math in this chapter is a percentage. So can you do part over the whole? If you can, then you're solid here. Okay. All right. So matter is anything that has mass and takes up space. If we ratio those two things, that is called density. Okay. We can look at properties of matter. As far as properties of matter are concerned, we can break those down into physical properties and chemical properties. So I have kind of a flow chart over there for you guys, and then I can draw it up here too. So we have properties as a whole, and we can break those down into physical and chemical. Physical properties then can be broken down into 2 additional categories, which is called extensive and intensive. Okay, so it's kind of a flow chart of what we're looking at today as far as our properties are concerned. So let's talk about what those different things mean. Okay, physical properties are very easy to observe. We can look at them and go, oh, okay, yeah, I can see that this stapler is blue, and I can see that this cell phone is a rectangle, and I can see, you know, you can look at the things and tell that. And you don't have to change what they are in order to do it. Okay? So if I take the mass of this, it's still going to be a cell phone when I'm done. Nothing's going to change about that. As opposed to chemical properties, which we'll get into in just a second. All right, extensive properties. I'll let you write some of these down in your notes, then we'll talk about them. Okay, good. All right, so extensive properties. What you need to do is you need to ask yourself, is an extra amount going to make a difference? So if I laid these popsicle sticks end to end and I measured their length, If I added 4 more to them, would the length increase? Okay, then that's an extensive property. An extra amount made a difference in that measurement. If I weighed these 3 popsicle sticks and then I added all of these popsicle sticks to it, would that make a difference in the mass, in the weight? Okay, those are extensive properties. Get the idea? Now, these things as a whole do not do well with identifying what the substance is. Okay, think of an object. I don't care what it is. Think of its mass. Think of its volume. Think of its length. Everybody's object in here had that, and everybody's object was probably different. Okay? It's not a good way to identify a substance. It is good for data. I mean, we need it for other things. We need it for other situations. But for identifying what that material is, it doesn't do well for us. Okay? In that case, we need to lean on intensive properties. Okay? And we'll talk about what they are here in just a second. All right, that's probably been about 5 minutes. I'm hot. I'm burning up. It's probably too loud for the recording. We're not getting in the air. Okay. All right. So if you ask the question, if extra makes a difference and it doesn't, then that's an intensive property. It helps to identify properties that are it helps to identify things that are pretty unique to that substance. So here's some examples. Okay. State of matter. If I describe a substance that is liquid at room temperature, has a melting point of 0 degrees, a boiling point of 100 degrees, its density is 1 gram per milliliter, it has no odor, it's not shiny, malleable, or ductile, its texture is wet, and it's colorless. What did I describe? Oh, okay. So a good set of intensive properties can help you identify what that substance is. Okay? These things, extra doesn't make a difference. Okay? It can be a cube of ice or it can be an iceberg. Okay? State of matter is irrelevant. It doesn't matter if you have a cup of water or a gallon of water. The boiling point is still going to be 100 degrees Celsius. It's still going to freeze at 32. Its density is still going to be the same. You got a cup of water, and you guys saw that with your lab, right? You had 20 milliliters, you had 40 milliliters, you had 60 milliliters. The mass changed, the volume changed. Did the density, or should it have? No. Okay, it did because we didn't have great lab technique. But the point is that density shouldn't have changed. That's an intensive property. Okay? All right. I forgot to add these 2 things into your notes. So make sure that you add them into your notes there as far as solids. I'll let you write them down and then we'll talk about them. Huh? So
wait, if mass and volume increase, why wouldn't the density increase as well?
Because it's a ratio of them.
Oh, yeah.
Remember? It's a ratio. So the ratio is still going to be the same.
I was thinking of...
Just like, when you had 20 grams of water, you had 20 milliliters. Well, when you had 40 grams of water, you had 40 milliliters. So the ratio, the 1-to-1 ratio stayed the same.
Okay.
So, have you ever been in like a church or some really old building, and you notice that the glass at the bottom starts to pool or get thicker? Have you ever noticed that before?
What?
Like if you're in a really old building, okay, and you try to look through the glass, okay, that glass at the bottom is like distorted. Okay,
Yeah.
it's not.
Which drawer?
I don't care. It's not that the glass was just, I mean, it may have been poor glass to begin with. We don't know that. It's so old. But it's because over time, glass is an amorphous solid. So over time, it starts to flow, and it's going to start to pool a little bit at the bottom. And so you're going to get this kind of wavy, weird kind of situation going on because it's moved. Okay. Now, why has it moved? Because when you've got crystalline solids like your salts, for example, those are in a set matrix. But your amorphous solids like this, they don't have that structure. And so they have the ability to kind of flow and kind of morph over time. Yeah.
What kind of solid would we be?
What are we?
Yeah, because I mean we're technically solid, but we also have like liquids and gases and stuff inside of us.
Yeah, I mean,
Would we be considered an amorphous thing because we're always changing and growing?
I don't know.
That's more biology.
Yeah,
That's fair.
I don't know. I'll send you across the hall in a minute over that way, and you can ask him. He's smarter than I am. So yeah, but that's the idea behind it. So wax, when you talk about wax, candles, for example, other examples, silly putty. Have you ever played with actual silly putty? Not Play-Doh, but silly putty, the stuff that it's like in an egg-shaped thing.
Yeah.
That's an amorphous solid. You know how when you go into a parking lot or a road or something, and there's been a crack there, and they take that tar and they kind of put it in the crack. That in the summertime, you kind of walk on it, and it goes like kind of sticks to your shoe almost.
Yeah.
That's an amorphous solid. So these are all amorphous solids. They're just kind of a little bit strange as far as their structure and their matrix is concerned. Okay. So solids have a fixed volume and shape. So we can actually look at the shape and we can say, oh yeah, or oh yeah, that's a rectangle, or that sort of thing. They also have a fixed volume. So I could take the volume of this, I can measure it. Liquids don't have a fixed volume, but I'm sorry, they do have a fixed volume, they don't have a fixed shape. Okay? And then gases are neither. Now, there is one other term that's, yeah, question.
What makes the difference between the amorphous solid as opposed to like a liquid with very high viscosity?
The viscosity, I would say that it's probably the amount of time that it takes to flow, I would guess.
My guess is that since an amorphous solid is technically still a solid, that the makeup of it is actually still like in a trying to bind together. But
Yeah.
like a liquid with high viscosity is just like,
And there's certain mixtures out there too that are kind of weird, like where do they fit? Like if you've ever played with that oobleck and glurch, for example, like the one that's cornstarch in water, like you hit it and it feels like a solid, but then you turn it and it flows. Those are like thixotrophic mixtures. I mean, there's some weird stuff out there that's kind of hard to categorize, but just as a general kind of idea is what we're not going to try to get into the anomalies any more than the amorphous. That's as far as we're going to go this chapter. Yeah.
putting in amorphous solid.
Again, that's a mix. It's one of those weird mixtures. I would classify probably that as more of a liquid, but again, I don't know. It probably is dependent on temperature too.
That's fair.
The warmer you get it, it's going to change.
I mean, most amorphous solids are also dependent on.
Well, everything is dependent on temperature. I mean, I can take the glass and melt it if I
Yeah.
get it hot enough. So everything, but we're kind of getting off on tangents here. So, But vapor is one that we come back to consistently. So if something is normally, Lawton, bring me that phone. The phone that you just put in your right pocket, bring it to me. So vapor is anything that's a solid or a liquid at room temperature normally. So water, for example, at room temperature is a liquid. But if it's in the gas state, then it's considered a vapor. So you boil water, the stuff that's coming up off of the water is vapor. Okay? They give it a special term, steam, when it applies to water specifically. But if we had gasoline, okay? Gasoline is normally a water or a liquid at, not water, but a liquid at room temperature, okay? What's going to be contained in the top part of your gas tank and your gas can is going to be a vapor, okay? And we're going to come back to that later this year when we talk about vapor pressure, okay? And things that are vapors. All right. So chemical properties then are the ability or inability of a substance to combine with or change into one or more other substances. Okay? So if you can observe the property, okay, and when you're done being able to make that observation, it's the same thing, then that was a physical change. If it changed into something completely different, chemically structured, okay, then that was a chemical property. Okay? So, if I have something and I set it on fire, huh?
Are you going to set something on fire?
No, I'm not setting anything on fire. You guys have seen stuff on fire. You just haven't seen what I'm about ready to do. So that's what I'm trying to do for you, something different. Okay?
Water on fire?
It's not exciting. No, it's not really that exciting. So
You
don't
can
get
set water on fire.
don't get too excited. Honestly. Don't get
You
very
don't need
excited.
gasoline.
Okay.
Just put mercury in the water. Not mercury, magnesium in the water.
So
It lights the water on fire.
flammability, okay? If something's flammable, that's a chemical property. Because if we observe that change by setting something on fire, we're not going to have the same thing left over. Okay? So, if I have a piece of paper and I set it on fire, am I left with paper? If I have a gasoline in that gasoline tank and I go through a combustion engine, am I going to have gasoline in the end? No. Okay? It's going to turn into water and carbon dioxide and carbon dioxide and maybe some other byproducts if the stuff isn't, pure. My truck right now is rusting because it's like 11 years old. Okay? Huh.
We're rusting. Our blood is oxidizing. We rust from the inside.
The ability to corrode. So have you ever seen batteries that have like the white crud on them after they've been in something for too long? That's corrosion. Explosions. You've seen fireworks before. Okay? This you haven't seen. Forming precipitate. Probably. Okay? So what a precipitate is in chemistry, as opposed to in earth science, which is rain or snow or sleet, okay? What it is in here is a precipitate is a solid that forms when you mix two liquid compounds together, okay? So I've got here, I have lead nitrate. So that's the formula for lead nitrate on the board up there. I'll write it on here for the folks at home, okay? So I've got a maybe. I will. Go. PbNO3. That's lead nitrate. Okay? I'm going to take this out. I'm going to put it in here.
Lead nitrate the same as lead nitrate have like the same toxicity like that.
Say that one more time, a little louder.
Does lead nitrate have the same toxicity to humans as normal lead?
Yeah, I mean, it's got lead ions in it. Now, typically lead to humans, it's not really that harmful to adults and people with our brains that are fully, don't take this the wrong way, but are fully done growing, okay? So your brain is still developing, okay? My brain is done. You know, it's not really changing much.
Yeah,
except maybe going downhill. But anyway. Okay, yeah, about the time you hit 25. And the earlier the development, the more the lead is going to make a difference. Okay, so the people that were affected, like in Flint, Michigan, with that lead crisis that they had, that was primarily the young kids, and it was their brain development. The adults, they didn't notice anything. Okay, it was just the kids that because it was the brain development that's an issue. So it's the lead is the concern for that. That's why they don't want kids eating lead paint. If the adults ate it, you know, there'd be some problems, but they're not going to have problems with their brains as far as development's concerned, okay? They might have problems because they're eating lead paint, but that would have been before they ate the paint, okay?
Because they ate paint when they were a kid.
But this is a clear liquid. Now I'm going to take this guy. This is the next one. This is ammonium carbonate. So I'm going to add these two clear liquids together. This is NH4 2CO3. Okay. So this is also a clear liquid. I'm going to add these two things together. Okay. And you'll see what happens here. It's nothing terribly exciting. You're going to see this. Oops, I'm spilling this all over the place. Okay. Do you see how that's getting cloudier and cloudier and cloudier? I told you it's not terribly exciting, but it's not a clear liquid anymore. Okay. It's cloudy. And if we let that set for a long period of time, I think this was from second hour, you can see that that solid is going to settle at the bottom. That solid, that white solid at the bottom, is called a precipitate. Okay? And we can see that this has gone through a chemical reaction because what's in this test tube now is not these things. It's actually lead carbonate. And we have ammonium nitrate. Okay? This is our solid and this is our liquid. And you guys won't know how to figure that out yet, but you will get there with me, okay? But that's the clear part is the ammonium nitrate. This is the lead carbonate. Yeah.
What are these chemicals used for?
I don't know. I'd have to look it up.
Okay.
In here, that's what I'm using it for right now is to show you precipitate. Okay. So these things you can identify, we can go through and we can identify what these are, but this is an indication, if we form a precipitate, that's going to be an indication that we went through a chemical reaction. Okay? Questions? All right. Tomorrow, then, we will pick up with chemical and physical changes. Tonight, you're going to flip into your notes, pass the notes, to your first worksheet. It looks like a chart. And while I clean up my thing here, you're going to work on that homework that's due tomorrow. Huh? Where's some more? Oh, there it is. All right.
Thanks anyway.
Trying to be a mom. Cleaning up. So your homework is 3-1 then, okay?